1898, the Cascade Range logging camps of Washington State. The engineering consensus from Philadelphia's finest locomotive designers could never have predicted what timber company foremen were witnessing in the mountain forests. Independent logging operations running crude geared locomotives built using methods that contradicted everything modern railroad engineering said was necessary for efficient timber transport. Through the steam and wood smoke of the mountain rail lines, stubby Climax locomotives crawled forward at 12 miles per hour, with reliability that seemed impossible to mainline railroad engineers. No boiler pressure exceeding 160 pounds, no sophisticated valve gear, no roadbed standards requiring graded ballast and precision track alignment. Yet they hauled massive log loads month after month through conditions that would derail sophisticated equipment within hours. Back in the engineering offices of Baldwin and American Locomotive Works, designers were perfecting the next generation of timber haulers. Larger fireboxes, higher steam pressure, more complex running gear. The future of logging transport would surely require more power, better engineering, faster schedules. The mountain operations were proving something completely different. Simple bevel gearing, flexible truck assemblies, forgiving suspension systems built for track crews with axes and hammers instead of precision instruments. 70 years later, those same logging engines were still moving timber, while modern diesel locomotives required complete rebuilds. The specifications arrived at the Climax Manufacturing Company's works in Corry, Pennsylvania in early 1892, with the kind of practical desperation that made conventional railroad men nervous. Independent logging operations wanted a locomotive that could navigate temporary tracks laid directly on forest floors, climb grades exceeding 8%, and negotiate curves so sharp that standard locomotives would simply derail. More critically, the machine had to keep running when the nearest railroad shop was 200 miles away and the closest boiler specialist was working for a competitor who wouldn't share knowledge. Charles Scott studied the requirements from his drafting table where prototype drawings were taking shape. As Climax's chief engineer, he understood that this design could define an entire category of industrial locomotives. But the engineering challenge seemed almost contradictory. Timber operators wanted hauling power and mountain climbing ability, yet demanded that any reasonably competent mechanic could maintain the locomotive using tools carried in a standard tool car and parts fabricated in camp machine shops. The solution emerging from Scott's engineering work violated nearly every principle of efficient railroad locomotive design that had been established over 6 decades of development. While Baldwin Locomotive Works chased higher boiler pressures and more sophisticated valve timing that promised increased horsepower per pound of locomotive weight, Climax engineers were deliberately simplifying everything. The standard Class B Climax carried a vertical boiler producing steam at just 140 pounds per square inch, operating with the modest, sustainable pressure of a machine built to survive decades in environments where catastrophic failure meant financial ruin. The revolutionary element was not the boiler, but the power transmission system that connected it to the rails. Scott's design mounted a 2-cylinder engine at an angle, driving a longitudinal drive shaft that connected to both trucks through bevel gears and side rods. Every wheel on the locomotive was powered, distributing tractive effort across the entire machine rather than concentrating stress on a single driving axle as conventional designs required. Railroad mechanical engineers examining the prototype drawings dismissed the approach as fundamentally inefficient. The multiple gear reductions consumed power that direct drive systems delivered to the rails. The flexible truck connections introduced mechanical complexity that standard rigid frames avoided. Most damningly, the entire concept seemed optimized for conditions that proper railroad construction should eliminate rather than accommodate. What the critics missed was the operational reality of logging railroads, where track quality was not a constant but a daily variable. Rails spiked directly to log stringers rather than ties, alignment that shifted with every heavy rain, grades that followed terrain rather than engineering standards. The Climax's flexible trucks allowed each wheel set to find its own position on uneven track, maintaining contact and traction where rigid locomotives would lift wheels and lose adhesion. The gear reduction that conventional engineers criticized as inefficient became the system's greatest strength in mountain logging operations. The bevel gears converted modest boiler pressure into massive torque at low speeds, allowing the locomotive to creep upgrade with log loads that would stall higher pressure machines. More importantly, the gearing was simple enough that camp mechanics could inspect, adjust, and rebuild components using techniques learned from industrial machinery rather than specialized locomotive training. William Barnhart watched the first production Climax locomotives leave the Corey Works in 1894 with the satisfaction of a works superintendent whose patents were about to prove themselves in the harshest possible testing ground. His vertical boiler design provided better water circulation on steep grades than conventional horizontal boilers, preventing the crown sheet exposure that caused catastrophic failures when standard locomotives tilted on mountain tracks. The entire machine embodied a philosophy that prioritized survival over sophistication, recognizing that in remote timber operations, a locomotive that ran slowly but continuously was infinitely more valuable than one that ran quickly between frequent failures. The Michigan-California Lumber Company took delivery of Climax No. 12 in April 1897 for their operations in the Sierra Nevada foothills east of Fresno. Logging Superintendent Frank Morrison examined the stubby machine with the skepticism of a man whose entire operation depended on equipment reliability. The locomotive looked nothing like the graceful mainline engines he had admired, its vertical boiler and exposed gearing suggesting improvised construction rather than deliberate engineering. The first assignment would test every aspect of Scott's design philosophy. 3 miles of newly laid track climbed from the mill yard to cutting areas at elevation, following a route that gained 600 feet through terrain so steep that surveyors had simply marked the most practical path rather than attempting to establish proper grades. The rail itself was 40-pound iron, spiked to 8x8 timbers laid directly on cleared ground, with curves estimated by eye rather than measured by transit. Morrison rode the locomotive's cramped cab as engineer Tom Rawlings eased the throttle open for the first loaded descent. 12 log cars, each carrying 8,000 board feet of sugar pine, represented a test that would either validate the Climax design or demonstrate its inadequacy. Conventional geared locomotives like the Shay used their gearing primarily for climbing, relying on air brakes and careful speed control for descents. The Climax's design allowed the gearing to work in both directions, letting the engine's compression brake the train while maintaining positive control. What happened over the next 4 hours established operational patterns that would define logging railroads for the next half-century. The Climax crawled down the mountain at walking speed, its geared drive providing such positive control that Rawlings barely touched the air brake. The flexible trucks absorbed track irregularities that would have derailed rigid locomotives, while all-wheel power distribution prevented the wheel slip that plagued conventional designs on wet rail. More significantly, the return climb demonstrated capabilities that surprised even Morrison's experienced crews. Where standard locomotives would have required helpers or multiple trips, the Climax ground steadily uphill with empties, its bevel gears converting modest steam pressure into relentless pulling power. The engine ran cool throughout the climb, its vertical boiler maintaining water level and steam pressure on grades that would have exposed horizontal boiler crown sheets dangerously. By the end of that first week, Michigan, California had revised their entire logging plan around the Climax's capabilities. Track could be laid faster and cheaper when precise alignment became unnecessary. Cutting areas previously considered inaccessible due to terrain became viable when the locomotive proved capable of negotiating temporary tracks that would be abandoned after the timber was removed. Most importantly, the machine required minimal maintenance beyond water, fuel, and basic lubrication, operating shift after shift without the constant attention that sophisticated locomotives demanded. The engineering choices that had seemed crude in the factory were proving their wisdom in conditions where survival mattered more than efficiency ratings. What separated the Climax from its competitors was not superior materials or advanced metallurgy, but a systematic design approach that assumed repairs would happen in primitive conditions by mechanics whose primary training came from agricultural equipment and stationary engines rather than railroad shops. Every component accessible for inspection, every wearing surface designed for field renewal, every critical system built with tolerances that allowed for imperfect repairs. The locomotive's operator's manual, published by Climax Manufacturing in 1898, reflected this philosophy in its straightforward instructions for complete field rebuilds. Bearing replacement, valve grinding, boiler tube renewal, everything a logging camp crew needed to maintain their locomotive indefinitely. The manual assumed access to basic machine tools, a competent blacksmith, and mechanics willing to fabricate parts when ordering from Pennsylvania meant weeks of downtime. Master mechanic George Hendricks had memorized most of the manual by his second season maintaining Michigan, California's growing Climax fleet. Working from a machine shop housed in a converted logging car, he performed repairs that would have required specialized railroad facilities for conventional locomotives. The vertical boiler design allowed tube replacement without removing the boiler from the frame, a task Hendricks completed in 3 days using tubes rolled in the camp blacksmith shop from standard boilerplate. The bevel gears that drove the trucks wore predictably and could be inspected simply by removing side panels that required no special tools beyond standard wrenches. When wear patterns indicated approaching limits, Hendricks ordered replacement gears from Climax, but discovered he could extend service life significantly by careful adjustment of mesh clearances, a procedure the manual described in detail with measurements achievable using feeler gauges and careful observation. The flexible truck assemblies proved their value not just in operation but in maintenance accessibility. Each truck could be dropped from beneath the locomotive by removing 4 bolts, allowing complete wheel set replacement or bearing renewal without the overhead cranes that rigid frame locomotives required. Hendricks developed a routine where one crew maintained the locomotive while another rebuilt trucks in rotation, ensuring that worn components were renewed before they reached failure points. This approach created an operational advantage that transcended simple reliability. Conventional locomotives required scheduled shop time that interrupted timber operations, with repairs following failure rather than preventing it. The Climax design allowed preventive maintenance that kept the locomotive running continuously, with component renewal happening during routine servicing rather than emergency breakdowns. The steam cylinders, mounted accessibly alongside the boiler, could be re-ringed and rebored using portable equipment that Hendricks operated inside a temporary shelter constructed next to the locomotive. The work required skill and patience but no specialized railroad machinery, allowing complete engine overhauls in logging camps that had no connection to established rail infrastructure. By 1900, this maintenance philosophy had created something unprecedented in industrial history. A locomotive whose useful life would be measured not in years but in decades, kept running by mechanics who understood that real engineering achievement was not building machines that never wore, but building machines whose wear could be managed indefinitely with practical skills and available resources. The first wave of retired Climax locomotives began appearing at equipment auctions in the 1920s as some logging operations mechanized or depleted their timber stands. But retirement proved temporary for machines built with decades of service life remaining. West Coast Lumber Company purchased 3 used Climax engines in 1924, paying $800 each for locomotives that had already logged 15 years in Washington operations. Superintendent Harold Benson examined the machines with the practical eye of a man who needed reliable power more than modern sophistication. The boilers showed wear but passed hydrostatic testing at working pressure. The gearing displayed predictable wear patterns that indicated proper maintenance rather than abuse. Most importantly, the locomotives had complete maintenance records showing systematic care throughout their previous service, the kind of documented attention that predicted future reliability. Benson's operations in coastal Oregon presented challenges that would test the Climax design in new ways. The timber was larger than Sierra pine, with individual logs weighing up to 15,000 pounds. The terrain was steeper and wetter, with track conditions that deteriorated rapidly during the region's legendary rainfall. Modern logging operations were adopting diesel tractors and truck transport, technologies that seemed destined to obsolete steam logging entirely. The Climax locomotives responded to these challenges by simply continuing to work. The flexible trucks that had handled Sierra grades managed coastal mountains equally well. The vertical boilers that had proven themselves on 8% grades worked reliably on 12% climbs. The geared drive that converted modest steam pressure into massive torque hauled the heavier coastal logs without requiring boiler pressure increases that would have stressed aging components. What emerged over the following decades was a pattern that would define these locomotives' legacy. They simply refused to wear out in ways that would justify replacement. Boiler tubes were renewed on regular schedules. Gearing was rebuilt when wear reached prescribed limits. Bearings were replaced as clearances increased beyond tolerance, but the fundamental structure, the frame and trucks and drive system, continued functioning with maintenance costs that remained economically viable even as diesel technology advanced. By 1945, West Coast's 3 Climax locomotives had each logged over 30 years of service between their original operations and their second careers. Benson had overhauled each machine twice, performing work that included complete boiler retubing, cylinder reboring, and gear replacement. The total cost of these overhauls, spread across 3 decades, remained well below what new diesel locomotives would have cost, even accounting for the Climax engine's lower productivity per hour. The maintenance records from this era revealed the wisdom of Scott's original engineering choices. Components wore predictably and could be renewed before failure. Systems remained simple enough that camp mechanics could perform major work without specialized training. Most critically, the locomotives operated in a middle ground of capability that matched logging railroad requirements better than either underpowered earlier designs or over-sophisticated modern alternatives. The same qualities that had made railroad engineers dismiss the Climax as crude were proving to be exactly what allowed these machines to survive decades beyond their expected service lives, operating in conditions that had not changed significantly since the 1890s. By 1965, the logging industry had largely abandoned steam power in favor of diesel locomotives that promised higher productivity and lower operating costs. Simpson Timber Company operated a mixed fleet that included both modern diesel equipment and 2 Climax locomotives that had entered service in 1903 and 1908, respectively. The contrast between these technologies would prove more complex than simple progress versus obsolescence. The new diesel switch engine delivered to Simpson's operations carried a price tag of $48,000 and represented current railroad technology adapted for logging service. The 6-cylinder diesel produced 240 horsepower through a hydraulic transmission that provided smooth power delivery and eliminated the steam locomotive's need for water and fuel stops. Electronic controls replaced mechanical linkages, and the enclosed cab offered operator comfort that open steam locomotives could never match. Operations manager Robert Chen watched both technologies work the same timber operations with the analytical attention of a man responsible for equipment economics. The diesel locomotive moved more loads per shift thanks to higher speeds and elimination of servicing delays. Fuel costs favored diesel significantly, with the steam Climax engines consuming cordwood that had to be cut and transported, while the diesel burned commercial fuel oil delivered by truck. But the maintenance equation told a different story. The diesel engine required specialized service that only certified mechanics could perform, with electronic fuel injection systems and hydraulic components that demanded precise adjustment and expensive replacement parts. When the transmission developed problems at 800 operating hours, the repair required 3 weeks at a railroad diesel shop and cost $7,000 for parts and labor. The Climax locomotives continued their established patterns of operation and maintenance that had changed remarkably little over 6 decades. Fireman duties remained labor-intensive, requiring constant attention to fire and water levels. Operating speeds limited daily productivity compared to diesel power. But when maintenance was required, Simpson's own mechanics performed the work using skills and tools that had remained relevant since the machines entered service. The comparison became stark when both locomotives required major overhauls within the same year. The diesel engine needed injector replacement, turbocharger rebuilding, and transmission service that cost $21,000 and required shipping the locomotive to specialized facilities. The Climax overhaul involved boiler retubing, valve grinding, and bearing replacement that cost $8,000 in parts and was completed entirely in Simpson's own shops using techniques documented in manuals published before World War I. Chen's operational analysis revealed economics that contradicted simple assumptions about technological progress. The diesel locomotive produced more revenue per operating hour when running, But its higher purchase price, expensive maintenance, and specialized service requirements created ownership costs that exceeded the steam locomotive's total expenses when calculated over equivalent periods. More significantly, the Climax machines had already demonstrated service lives exceeding 60 years, while the diesel manufacturer projected a 15-year economic life before replacement. The engineering philosophy that had seemed obsolete was proving its enduring relevance in the arithmetic of industrial operations, where machines that ran reliably often outperformed machines that ran faster but required more expensive support systems to maintain that performance. 1978 marked the end of commercial steam logging in North America when Cascade Timber shut down its last operational Climax locomotive after 71 years of continuous service. The machine had entered service in 1907, hauling Douglas fir in Washington, survived 2 ownership changes, and logged an estimated 350,000 operating hours moving timber through conditions that had destroyed countless other locomotives. The final shutdown procedure followed protocols that had changed remarkably little over 7 decades. The fire was drawn and the boiler drained. Steam fittings were loosened to prevent damage from condensation. The gearing was lubricated for storage. The entire process took 2 hours and required no specialized equipment beyond basic hand tools and an understanding of steam locomotive fundamentals that any competent mechanic could master. What made this particular locomotive remarkable was not its longevity alone, but the maintenance records that documented every repair, every component replacement, every overhaul across 71 years of service. The boiler had been retubed 4 times, with the last retubing in 1968 using tubes fabricated to original specifications by a boiler shop that had never previously worked on logging locomotives. The cylinders had been rebored 3 times, with the final bore exceeding original diameter by 2 inches, but still maintaining adequate wall thickness for safe operation. The bevel gears that drove the trucks had been replaced twice, in 1931 and 1962, with both replacement sets manufactured by small machine shops working from original Climax drawings rather than from the long-defunct Climax Manufacturing Company. The flexible trucks had received new wheel sets 5 times, with bearings renewed on schedules that prevented wear from reaching failure points. Every major component had been rebuilt or replaced at least once, yet the fundamental locomotive remained recognizably the same machine that had left Pennsylvania in 1907. Museum curator David Morrison examined the locomotive during acquisition discussions with a historian's appreciation for industrial archaeology. The machine represented not just logging history, but a complete engineering philosophy that had proven itself across an era that had seen transportation technology transform from steam to diesel to electronic control. The Climax had survived not through superiority in any single performance metric, but through systematic design choices that prioritized maintainability over sophistication. The documentation that accompanied the locomotive told the story of practical engineering applied to brutal service conditions. Maintenance logs showed systematic attention that prevented catastrophic failures through preventive component renewal. Parts invoices documented a supply chain that had adapted as original manufacturers disappeared, with machine shops fabricating replacements from drawings and measurements rather than standard catalogs. Training records showed knowledge transfer across 3 generations of mechanics, each learning from predecessors who had maintained these machines since the steam era's beginning. The final tally of this locomotive's economics revealed numbers that would have seemed impossible to engineers designing modern equipment. Total maintenance costs across 71 years, including 4 complete boiler retubing, 3-cylinder rebores, 2 gear replacements, and countless minor repairs, totaled approximately $112,000 in contemporary dollars. Operating costs, including fuel, water treatment, and routine servicing, averaged $18 per operating hour across the entire service life. The locomotive had moved an estimated 15 million board feet of timber and operated reliably enough that unscheduled downtime remained below 5% throughout its working life. The engineering philosophy that railroad designers had dismissed as crude had created something genuinely remarkable. A machine that survived 71 years of brutal service because it was built for one purpose: to endure what no other locomotive could, maintained by ordinary mechanics, using ordinary tools in conditions where sophistication meant failure and simplicity meant survival.